Al-Sibai from the Faculty of Engineering at the University of Beirut in Lebanon. And Ryan will give us a talk about a new cloud service for water distribution network monitoring. So we can launch the video presentation or the presentation of Ryan. I don't know if Ryan is present here in the meeting, or one of the colleagues of the first papers, of the authors of the.
Hello everybody. I am going in this video to present our paper entitled A Cloud-Based Foundational Infrastructure for Water Management Ecosystem. In this presentation, we are going to discuss the following main points. At first, we will introduce our work, and then we'll talk about the problem of our work. Then we will discuss our contribution. We will talk mainly about what we call central monitoring system and native filtering as a service solution, which is actually the solution that we propose in this paper. And finally, we will conclude our work. So ICT solutions for water management are highly important as a global initiative. ICT solutions such as, for example, intelligent water management systems, dynamic water pricing systems, peer-to-peer water trading systems, and e-agriculture are at the core of UN's sustainability goals and are becoming very hot research topics. The development of efficient ICT solutions for water management relies on continuous updates of accurate and timely information. It's inefficient actually and not practical to require every ICT solution to collect and to process a huge amount of data streams in order to perform a specific task or to reach the goal. The overhead resulting from adding a water monitoring component to every water management system is simply too expensive. Thus, in this paper, we are interested in designing an intelligent water monitoring service that helps in complementing the water management ecosystem and facilitates the development of ICT solutions for water management. The designed service collects, processes, and delivers accurate and timely and dynamic and cost-efficient data through standardized interfaces to the systems needing it. To do so, we propose in this paper a new cloud service that offloads the complexity of the central monitoring system with all its overheads to the cloud. This service supports new business models and an ecosystem that can be created around the generated data while providing water network operators with a plethora. So, in this work, we showed the infrastructure requirements for a functional central monitoring system. These requirements can be really a problem and an obstacle facing the deployment of a water monitoring system by states, NGOs, or private initiatives in developing nations who are actually in desperate need of such a system. The calculated infrastructure includes the computational resource required to run the central monitoring system, which is responsible for data cleaning and summarization, and the number of servers needed to ensure high availability of the service. The used dataset that we are using in this paper is generated from the water sensors deployed in the Paris region in France. And the recorded data of these sensors are structured data streams that have both spatial and temporal characteristics. Each record observation is composed of two fields, the recording date of the measure and the value of this measure, which is the water consumption volume. These data are generated in a regular manner by the sensors with a frequency of one observation each 15 minutes. The execution time of the sampling process includes the time of reading, sampling, and writing the data in the summary, and is dependent on the following factors: the number of received observations for each stream, which depends on the stream rate or frequency of the sensor, and the number of streams received, the sampling rate, the window size, and finally, the sampling technique applied in order to summarize the data. We evaluate in the first figure, as you can see in this slide, the execution time taken by the central monitoring system to construct and to build a summary for each received data stream using some sampling algorithm. Of course, more details about these algorithms can be found in our paper. You can notice that the execution time of the sampling process increases in a linear manner with the increase of the number of streams to be processed and summarized. The second figure in this slide represents the cleaning process time, and the time that we need in order to clean the data received by the sensors. You can conclude that the cleaning time needed is not linearly dependent on the number of received streams. In fact, for a single data stream, this cleaning time depends on many parameters, such as, for example, the number of received observations, the amount, and the distribution of missing data and outliers. And as these parameters are variant from one stream to another, the cleaning time cannot be predicted in advance. Increasing the availability of a system involves maximizing the percentage of time during which the system is operational. To protect the system against non-expected overloads and to avoid the system balancing, balancing can be used to ensure high availability. Ensuring high availability consists of actually of using a set of servers in which the incoming streams are distributed to help reduce the load on a single server. We show in this picture in this slide the calculated number of servers needed to run the central monitoring system while ensuring high availability for the stream rates discussed in the paper. As shown in this picture, a local small-scale monitoring system of about 1 million sensors requires a data center of about 253 servers for stream cleaning and processing. This data center is too expensive for private initiatives, NGOs, and states to install and to operate and to maintain. Okay. Thus, water management systems relying on the data generated from the monitoring system will be jeopardized as well. To provide states and NGOs and private initiatives the possibility to deploy a water management system without the burdens of water monitoring systems, we propose in this paper a new cloud service called Native Filtering as a Service, which is presented in this slide. Sensor data streams are arriving actually at a high speed, and they produce a huge amount of data, impossible to store in due time. On their side, erroneous and inaccurate and inconsistent data cause much damage as for the supervision and detection of abnormal data in the monitored network. It is therefore necessary to filter these data on the fly and to store only those that are relevant by producing summaries. Native filtering consists of filtering in a quantitative and qualitative manner and real-time the received sensor data in order to overcome the poor data quality and the huge amount of data received. The native filtering process, as you can see here, consists of two sub-processes: the cleaning filter, what we call also a qualitative filter, and the sampling filter, what we call also a quantitative filter. When the qualitative filter receives the data from the sensors, it proceeds to check and to improve their quality. Thereafter, the data are summarized by the quantitative filter. Native filtering as a service, abbreviated as NFAAS, consists of providing the cleaning and sampling filters as services via cloud computing. Therefore, clients can access and benefit from the cleaning and sampling applications over the internet when they need this with a payment based on their use. Once the data are clean and summarized, it is essential also to store them so that they are available for future analysis either by their owners or by other users interested in these data. Of course, the visualization of the obtained data analysis result is essential in order to help the network administrator to understand the monitored environment. That is where the big data as a service comes in. Big data as a service provides the user with a remote cloud storage server to store and edit their summaries, as well an analytic platform for the analysis of these summaries and the visualization of the results. The cloud-based sensor data stream processing flow is shown in this figure. Every instance of the native filter as a service has its own geographical coverage and specialized analytics and scope. Water management systems may be also interested in retrieving data from multiple native filter as a server instance, and also multiple native filter as a server instance can store their output on a blockchain, as you can see here, and this provides endless options for an ecosystem of brokers, regulators, investors, and innovators. So now we will talk in more details about these two services, the main two services, cleaning as a service and sampling as a service. So data analysis results depend on data quality. However, sensors data are often of bad quality. Since the conclusions and decisions that the network administrator will take are based on the data, this can lead to erroneous and faulty results and decisions. One solution is to assess the quality of the data and to improve it in order to make sure that the conclusion and decisions are correct. Our solution to clean the data and to improve the quality of the data is based on the total data quality management methodology. In this methodology, at first, the data quality dimensions are defined and measured, and then a set of quantitative metrics are produced. Finally, several actions are taken in order to enhance the data quality. The cleaning as a service improves the quality of the data in terms of mainly accuracy and completeness dimension. Okay. So the cleaning as a server deals with the problem of inaccurate and missing data. The cleaning as a service also delete and regenerate again for erroneous and missing data. And finally, add some quality statistics on the raw data. The quality dimensions that we are interested on in this paper and in our application are the following: the accuracy dimension, the sensor reliability dimension, the completeness dimension, and the confidence dimension. Here in this slide, you can see how we can calculate each one of these dimensions. Regarding the sampling as a service, the service aims to summarize and to reduce the volume of the received data. Once the data quality or once the quality dimensions of the received data are evaluated, the cleaning filter proceeds to enhance the data quality by, as we said, deleting erroneous and duplicated data and replacing erroneous and missing data. Then the native filtering solution will apply different sampling algorithm in order to summarize the qualified data and to construct finally what we call a summary. The build summary is now generated from the cleaning as a service are actually sources of big data as a service. They can be published on the cloud, allowing their owners to get a return on investment. Data is actually a very important asset for every organization, and the intelligent use of data can help make decisions based on real facts, and thus improve the business process by minimizing the risks and increasing the business in general. The concept of data as a service is that the data, regardless of its source and type, can be cleaned and integrated into a centralized infrastructure and made available to different users and applications on the cloud. In this way, data as a service allows the user to obtain the appropriate data and to use it directly to meet their needs, and the data owners to get a return on investment. So to conclude our work, water monitoring is a critical challenge for humankind. Since we share the same globe, breathe the same air, drink the same water, and share the same DNA, we are not short on solutions, but we are in desperate need of practical ones that are implementable in developing countries and areas. Successful solutions are not necessarily the most technically advanced, but the ones with successful business models. In this paper, we proposed a water monitoring cloud service that facilitates the development of needed water management systems. The strength of our proposal is that it is multifolded. It doesn't rely on the government's maintenance, which can be very inefficient in developing country. And also, the second strength of our proposal is that it creates an ecosystem around the generated data, which can help develop the areas using these services. And thank you.
Okay, thank you for the video presentation. So I think that we have one question. It's about the slide number 10. The question is, which sort of actions is proposed here?
Sidi, maybe I will go on with the question. It's more, thank you for the presentation first, but it's more about use case, practical example of the service. Have you already some developments and use cases of the proposed methodology?
Yeah, I see. Okay. So first, I want to add the context of this work. In fact, it was done in the context of a French project with many industrial and academic partners. And the leader of this project was Suez, who is responsible for water distribution in many cities in France, but also all over the world. So Suez receives continuously data streams from different sensors in their water distribution network. And these sensors can measure many information, such as the water flow, the instantaneous water flow. And we have first to deal with the data quality. In fact, we have to detect missing or erroneous data. As an example, we have many information about the water distribution network, and we can calculate, as an example, the maximal flow rate that we compare to what we receive, and we detect some anomalies. That's what we developed, and so Ryan was my former PhD student. She defended her thesis 2 years ago. Mm-hmm. I mostly supervised the centralized version of the platform that she developed, and then the distributed part, she did it after her thesis when she went back to Lebanon. It was with other supervisors.
Thank you very much for the explanation. Okay.
Okay. I have one question. it was about, because you talked about the resource requirement of a cloud applications. How do you predict this resource?
Yes, I don't have many details about that, but I know that Ryan used Rackspace in her implementation. In fact,
okay, some tools for doing that. Okay.
Yeah, this is the main tool to.
Okay. Thank you for the presentation and for the response of questions. Thank you very much. So we can move to the third presentation. I don't know if he is here. I have to check. Okay, so the third presentation will be given by Mohamed El Ghumari from the University of Hassan II in Casablanca in Morocco. And the title is Multitask Offloading and Computational Resource Management in a Mobile Edge Computing Environment. So if Mohamed is here, you can start presenting, or one of the coders. I have to check Mohamed. I don't think that Mohamed is here.
So maybe you can ask some code, or I don't know.
Yeah, Mohamed, there is Mohamed Youssef.
Hi, everybody. I am Mohamed Ghumari. I will present our work with my team in Lian Laboratory in FSDM phase with our supervisor, Professor Mohamed Oussama Sharqawi Malki. Our work is entitled Multitask Offloading and Computational Resources Management in a Mobile Edge Computing. As an outline of this presentation, I will start with the introduction and motivation. Then I will present our systems model, the problem formulation, the optimization problem are then exposed. After that, I will present how we could resolve this problem. Then I will show our proposed solutions and evaluation. At the end, I will conclude the presentation and state our perspectives. I will start by the following observation. Currently, smart mobile devices have become the main equipment of everyday life. They use applications that are demanding in terms of computation, resources, energy, and time. But with the following constraints: limited computation capabilities and limited battery lifetime. Then the computation offloading technique. With this new technique, processing and data storage are deployed out of mobile devices into a more powerful and efficient nearby IT infrastructure. Example, video encoding application that requires heavy processing that drains the battery of a smart mobile if it is made on its local processor. Then mobile edge computing. Mobile edge computing, it is a network architecture in which storage, resources, processing, and services are placed closer to the users, which means getting the cloud near the users. The secret is services proximity. This figure illustrates an augmented reality application example. Using mobile edge computing has many advantages. Low offloading deadline compared to mobile cloud computing, more confidentiality, and local execution energy gain. But we have to consider the following disadvantages. Overload of the access network. Now I will move to our systems model. This figure shows a single smart mobile device containing offloadable multitask list and edge server that can execute the offloadable task that are transmitted from the SMD. In our model, we have a list of n tasks. Each task is characterized by the following two parameters, dA and lambda A. dA, the amount of the input parameters and program code to transfer from the user's local device to the edge server. Lambda A, the workload referring to the computation amount needed to accomplish the processing of this task. Also, we have the SMD frequency FL between FL min and FL max. The edge server frequency must be between 0 and Fs. Local energy L must be less than max, and execution time TL and TO must be less than Cmax. Now we will move to the problem formulation. In the problem formulation, we use the following notations. Xi represents the execution decision for a task. Xi equals 1 offloading equals 0 local. Then the processing TL, the processing time for all tasks performed locally by the SMD itself. TO, the processing time for all tasks performed by the edge server. Consequently, the total energy consumption while executing all tasks that were decided to be locally executed in the SMD is given by AL. The execution energy for all the offloaded tasks is AS. The final energy consumption is obtained as AL plus AS plus AC. The final processing time is obtained as TL plus TO. Here we formulate our optimization problem, which aims to minimize the trade-off between overall energy consumption and overall processing time in the offloading process while maintaining the life of the battery. The problem obtained is formulated as CTA, where alpha plus beta equals 1. Now we will move to the obtained optimization problem. The obtained problem is formulated as follows. Now I will present how we could resolve this problem. To resolve this problem, we use the following notations: A0, C0, and lambda 0. Then problem P1 is decomposed into the following two problems: CTA1 and CTA2. This algorithm show how to obtain FL starts the optimal frequency. The second algorithm show how to obtain the FS starts the optimal frequency. Now I will present our proposed solutions. The third algorithm illustrates the pseudocode of our simulated aniline-based solutions. In this algorithm, we start by initializing a random policy. Then we use Kmax iteration. In each iteration, we pick a random policy X in order to improve the final trade of energy time. This algorithm illustrates our second proposed solutions. As experiments setup, we use C++ language and the following parameters. For the simulated aniline method, the following parameters values are adopted. This figure shows the results of the MHO solution are better than those of HO for all values, for all n values. The result of the first represents again the 1%. This figure shows a comparison between three situations with n between 2 and 50. All tasks are offloaded to the edge node. The offloading decision is done using our MHO solution, or all tasks are executed locally. This figure illustrates the execution time comparison for all the Bouts method with n is between 2 and 50. On the one hand, the HO curve illustrates a near linear running time that starts from 0 and reaches 0.5 milliseconds. On the other hand, the HO curve illustrates a near linear running time that starts from 0.5 milliseconds and reaches 170 milliseconds. Thus, this last figure showed the performance of the HO solution compared to the MHO in terms of decision time. In this paper, we studied the trade-off between energy consumption and task processing time for a MEC network. The SMD intends to offload optimally the contents of a list of heavy tasks as much as possible. The obtained results are very encouraging. In addition, the proposed solution performed the offloading decision within acceptable and feasible time frames. As future work, we will generalize our study to the case of multi-users. Thank you for your attention.
Okay, thank you for the presentation. I don't know if someone, the author or coders is present here. So we can ask questions if somebody is here. If not, we can switch to the next presentation. I will check. I have a question, but unfortunately there is no person. Is Sarah Maftah? Yeah, we have two questions, but unfortunately, I think that the others are not present here, so we have to switch for the next presentation. Maybe if the other will come after, they can answer if they want. Okay, so we can switch to the fourth presentations, which will be given by Rim Duha, which prepares her PhD under a joint supervision between University of Mons and INSEAD at Morocco. And the title of the presentation is the deployment of containerized deep learning applications in the cloud. So we can launch the presentations. Rim, if you are here.
Yes, I am here.
So welcome. So you can start. Yeah, you can start.
Okay. So, hello everyone, I am Rim Duha from the University of Mons, Belgium, and University of Mohammed V, Morocco. I will present our accepted paper entitled of Deployment of Containerized Deep Learning Application in the Cloud. So, the cloud computing has got an increasing importance in several domains where thousands of dedicated servers are set up to give the best service for their users on demand. In addition, these services are automatically managed by the providers, which require minimal effort of users. Many developers have transferred their working environment completely or partially to the cloud infrastructure in order to get more performance and reduce the complexity of installation and configuration. However, deploying application in the cloud is not necessarily easy, as the application include dependencies, are linked to different databases and integrate with different components and other services. This is particularly the case with artificial intelligence applications, which require significant competition resource and a huge amount of data to accelerate the learning of their models. So the migration of application to the cloud or inter-cloud is not obviously easy as it seems. Taking the example of a small company or a developer who want to migrate their development environment from the local to the cloud. So the developer will allocate, of course, his infrastructure, install dependencies, set up the necessary packages, and after several tests, the developer will realize that the resources chosen are not adapted to these needs. So he will decide, of course, to migrate to another infrastructure more suitable, therefore repeating all the installation process and setup of the application, which will result wasted in time, cost, and energy. The idea is to isolate the application from the infrastructure running on it to meet the portability needs and to make the migration process more easy. So, virtualization and containerization are the technology to create a set of isolated environments from the infrastructure. These technologies are used to run applications on independent way from the infrastructure, but containers are still the most widely used technology compared to virtual machine, because a container is lighter than virtual machine and it only includes the executable and dependencies. Also, several containers can share the same operating system, while a virtual machine contains a complete operating system, with its binaries, packages, and driver software, as well as the application itself. So, the development of application in the cloud must be increasingly modular, interoperable, and distributed. So many new technologies such as Docker container are helping to isolate the application from the infrastructure. With the expansion of containers, it's important to automate containers management, as hundreds and thousands can run in distributed servers. And manual management, of course, cannot handle to work on such environments. So Kubernetes, Docker, Swarm, Apache Mesos represent the three big technologies in container orchestration. These technologies offer several advantages to manage and orchestrate the applications. There are many work in the literature that have proposed container-based infrastructure using these technologies in order to have a self-adaptive architecture design that involves as needed. So we had selected the more interesting works that was based on defining cloud infrastructure based on container. For the first, their goal is provide the reuse of free services deployed by other applications, provide a maximum of agility and scalability, doing the abstraction of the underlying infrastructure, and having the ability to deploy the application on several infrastructure. For the second paper, their main goal is having an environment that automatically evolves according to the need and hosting various dynamic workloads. And for the next one, their goal is offering a high availability of microservices and reducing container failure resiliency time on Kubernetes infrastructure. And for the last one, they did the comparison between an infrastructure using Swarm and Kubernetes, and also facilitates the deployment and the scalability of the application. So as we can remark that the analyzing of application needs before the deployment of application are not included in their works, and this is an important task. Okay, so let's take this example of having 5 applications to be deployed in the infrastructure. So the white applications don't need a HPC, a high performance computing resource, to be executed. And the black one, it's a deep learning application that needs HPC resource. And we have 2 worker nodes. The first worker node is with GPU and the second worker node is with CPU. So if we want to deploy the application using this technology, okay, I didn't mention that here we take the example of default configuration of Kubernetes to deploy application, and note also that the other services like Mesos and Swarm have the same process. So if we want to deploy the application using this technology, the master node will check the worker node 1 and the worker node 2 if they have enough resource. If it has enough resource, the application will be deployed on it. Supposing that the first application will be deployed in the first worker node. Same thing for the second and third. And when we will arrive to deep learning application, the worker node having GPU doesn't have enough resource. So the application will automatically be deployed in the second worker node. So the application will be executed, but it will take a huge time. And this is the main goal of our proposed work, is analyzing the application before its deployment. So the proposed cloud architecture is composed of 3 machines, 1 with GPU and 2 with CPU. This is the characteristic of our machines, but our architecture is flexible for all types of material. Let's pass now to the software used. First of all, is Kubernetes. It's considered the most powerful orchestrator. It has the most feature and supports all major containers technology like Docker, RQT, Windows Container, and also is easy to use comparing with Mesos. We used also Docker. We use Docker as a container tool. Docker is the most popular tools for containerizing application. The motivation of using Docker because it represents the default container engine used by Kubernetes. And of course, we used Ansible is the IT automation tools. It can configure system, deploy software, and orchestrate more advanced IT tasks. Ansible is simple and easy to use, and it also has a strong focus on security and reliability. And finally, we use Slurm for managing and allocating the access to resources for users. So our infrastructure was configured in the cluster of University of Mons, and Slurm is already configured in our cluster. This is why we use this technology. So the proposed cloud architecture is based on containerized environments using Kubernetes, Docker, Ansible, and Slurm. And our infrastructure is composed of 3 physical machines, node 1, 2, and 3, and are sharing the same network. First, we started by deploying Kubernetes in our local cluster. So the master node is responsible for exposing the application, scheduling the service, and managing all the cluster. When a host fails, master node automatically restarts the failed containers to ensure the availability of the application. In our architecture, we use Docker to containerize and deploy application. Thus, for provisioning, orchestrating, and managing the configuration of our infrastructure, we used Ansible. Its role in our architecture is allowing the installation of needed tools, update or upgrade environments, start or stop services, change configuration, add groups, create users, log in log users, and give rules to implement the security and protect the privacy of each user account. All these process and configuration are managed by the master node. Our infrastructure needs also to offer a shared access to resources, so each node should have a limited resources in processor and memory. At a given moment, the node may only be able to execute a limited number of tasks. In order to meet this need, we used Slurm technology to manage and reserve the necessary resources for the proper functioning of each task. So in order to make our infrastructure smarter and automate the deployment of application in the appropriate node, a first analysis of deep learning application was carried out, and it should of course be improved. This study will allow us to integrate a script that will automatically assign the application in the appropriate infrastructure depending on its needs. So we start by analyzing the requirement need of RAM, CPU, GPU of each step of the deployment applications in order to limit the waste of the available hardware and allocate in a convenient and smart way only the suited resource for each deployed application. So to analyze the requirement need, we calculate the running time and memory consumption on GPU and CPU. For this aim, we used Python model for time calculation and memory profiler. That analyzes the memory consumption line by line for Python program, and it helps also to identify the high and the low intensive parts of the program. As a use case of this study, we use image classification for fire detection and personal object localization using deep learning models. These applications are developed using Python as programming language, OpenCV as computer vision library, TensorFlow, and Keras as deep learning framework, and we set for the number of epoch 10, database image 500, and so on. So, as shown in the figure, the use of a GPU is very important for training deep learning models, which require a high intensity of computation. We extract here a part of the results between 0 and 400 because the execution time was very important when running in CPU. The use of GPU for training phases is highly recommended since it's allowed to reduce computing times by a very important factor compared to the CPU. On the other hand, we can see that the use of GPU for the test and inference phases require a high consumption of memory compared to CPU, with a negligible gain of time execution, just some few of seconds. Based on this first analysis, we configure our platform to affect training for GPU and inference for CPU. So to summarize, in order to deploy an application in our environment, it will pass through several steps. First, the application should be containerized with suited configuration, assign the user to the appropriate node according to its requirements, and at the end, deploying and executing the application using Kubernetes. So I will conclude. We presented an architecture to deploy deep learning application based on container. As a first step, we started analyzing deep learning application needs by comparing between CPU and GPU in the case of training and testing models using two metrics, execution time and memory consumption. And we included a script in our infrastructure to deploy application depending on its types. As a future works, we are working on deployment of new deep learning application and also extending the comparative analysis needs of the application by deploying deep learning application in different cloud providers. And at the end is developing a generic script to select the suited infrastructure to deploy our deep learning applications. Thank you.
Thank you, Rim, for the presentation. So I don't know if there is some questions. You can ask question or only write questions in the chat if you like. Okay, if not, I have one question, Rim. So my question is about the architecture. Can we use some other kind of resources such as TPU, Tensor Processing Unit, within your architecture?
Yes, of course, we can use another resource as TPU. Now we just do the test for CPU and GPU, but we are planning to use another resources.
Yeah, the idea is that if you want to use some other kind of resource, we have not to change the architecture.
No, we don't need to change the architecture.
You can keep the selected choice and technologies can be kept in this changement. Okay. Okay, so thank you, Rim. If you have no questions, so we can switch to the fifth presentation, which will be given by, I will check, by Jonas Kruger Svensson from the University of Oslo in Norway. And the title of the presentation is Autonomous Provisioning of Preemptive Instance in Google Cloud for Maximum Performance per Dollar. So I think that the author is present here. So you can start the presentations if you are ready. Jonas, maybe Jonas.
Yeah, I'm responsible for this, but I asked to send the video. I think they will. Yeah, there it is.
Okay. Okay, we can send the video and you can answer the questions.
Welcome to this presentation. Hello and welcome to this presentation on autonomous provisioning of preemptive instances in Google Cloud for maximum performance per dollar. I've done this work together with my colleagues Jonas and Anis at the Oslo Metropolitan University. The basis for this work is that Google and Amazon and others rent out surplus computing power for a discounted price. Google calls this preemptible VMs, while Amazon uses the name spot instances. And the research question we are trying to answer with this work is, to what extent can the cost of batch computing be reduced using an autonomous algorithm that distributes workloads within data centers in different regions? Yeah, the Google Cloud Engine has so-called preemptible VMs. And different from normal VMs, you may risk to have a 30-second shutdown notice at any time, and then the VMs just shut down. And you have a maximum rental time for 24 hours. So these are the downsides to these VMs. The upsides is that they are up to 80% cheaper than standard VMs. Also, a basis for this work is that the Google Cloud Engine comes with an API. So using this client, we can control the VMs and start and stop them. Yes, Google Cloud Engine is spread all over the world in so-called regions. So at the time of the experiment, there were 15 regions, but there are the number is increasing from year to year. Yeah, at the time of the experiment, there were 15 regions, and for the experiments, we used VMs with 2, 4, 8, or 16 CPUs. There were some restrictions on using these VMs for standard accounts, and that was a maximum of 64 CPUs available worldwide. And for each region, there were at most 24 CPUs and 8 public IP addresses. Initially, we looked at the prices for these VMs. And you see there is a huge difference between the preemptible ones, which are roughly 1/4 of the price of the normal VMs. This is for 2 CPU VMs. We also did this for the other kinds of VMs, and you can see the 16 CPU VMs naturally are the most expensive ones. But not necessarily the cheapest when it comes to how efficient they are. Yeah, as we saw, there were some restriction on the usage. So what we want to minimize in this problem is the costs. So C is the cost of each VM in region R with a number of I CPUs. And then we had these restrictions, totally 64 VMs, and for each region just 24 VMs, and at most 8 CPUs. The workload we used, it could be any CPU intensive workload, but we chose to use cryptocurrency mining. and we used the MinerD cryptocurrency software and mined Moneros. So the idea was that these mining should run all the time, and we should pay as little as possible for doing as much work as possible. And technically, we used Docker containers to do all the works. And the performance was measured in hash per second. Yeah, so inside these containers, we had some scripts which all the time updated the databases with prices and with the efficiency so far. Yeah, initially we also measured the average hash per second for all the various VMs, and as we can see, there is quite a large difference. So part of the idea of this work is to pick the VMs at any time which are most efficient, meaning producing most hashes per second. Yeah, and this is an overview of the whole setup, where there are three important parts. Obviously, the most important is Google Compute Engine, which with the Cloud API we can run these scripts. This is the master, and here we run scripts which both collects all the data and controls all the VMs. And the second part, or the third part, is the Docker containers. So they run inside VMs. And inside these containers, the MinerD software is running, and also Python scripts which all the time updates the databases with the latest results. Inside the Docker containers, we have several scripts. Obviously, we need to run the miner once it starts, and we need to calculate the hashes and update the databases with the results. Then we have a central master VM which controls everything and actually stops and starts the Docker containers all over the world. So there are several automation scripts and scripts for killing instances and creating instances. Yeah, so the purpose of the master server, it has several purposes. It hosts two databases. It constantly updates prices in the database, calculates the dollar hash, and based on the current prices, it spawns VMs in Google Cloud. And part of the idea is then that it should shut down the most expensive VMs and start cheaper ones. So there are two main algorithms which does this. Central to the setup is the global price and efficiency. So the prices are fairly constant, but they can change from time to time. But the hash per second can also vary, and both this is taken into account when deciding where to run the VMs. Yeah, and this is a simplified version of the spawning VM algorithm, which has to be restricted to these restrictions we mentioned. There is also a database where for each VM, where you see the price per hour and dollar per hash for this VM. And this is the algorithm which checks this database and decides whether to keep a VM running or shut it down and start a cheaper one. We did a 72-hour experiment. This is what it looked like when we were running the experiment. VMs were started and stopped, but roughly there was somewhere between 15 and 20 VMs running at all time. This is the number of VMs spawned or started during the experiments. So some 8 CPUs VMs were started, and some 4 and some 2. And all the time VMs were also stopped. This could be due to the algorithm or due to Google shutting down the VMs, and then we had to find new ones. Or the scripts had to find new ones. Most of the time, the reason for shutting down VMs was that Google just closed down the VMs. But sometimes the algorithm found better VMs and shut down the running one to find a more optimal solution. Yeah. This sums up what we found, and what we found was that we were able to reduce the costs compared to a manual scenario where you just, as usual, you buy VMs and rent them for 3 days. While doing this using our autonomous scheduling algorithm, we were able to reduce the costs by 2/3. So the result was that the cost was only 33% of the normal costs. Well, mining cryptocurrency is, at least from this, not very profitable because we were able to mine Monero's worth of $14, while the actual cost of running all the VMs for 3 days was $56. So in this case, this was not profitable. But that was not the purpose of this work either. The idea was to make it as cheap as possible to do a lot of CPU work. As for related work, we have previously published a couple of papers. One is cost-efficient batch processing in Amazon Cloud with deadline awareness, where we utilize Amazon Spot instances. Another one is on automated cloud bursting and hybrid cloud setups using Apache Mesos, where we also use Amazon Spot instances. As for future work, one idea is to extend the current work to also include batch computing with deadlines. Another approach is to try and reduce energy consumption in batch computing by minimizing the amount of energy needed to process a given workload. And also including Amazon Web Service Spot instances could be a very nice way to extend the current work. Now to conclusions. Yeah. Given a set of Google Cloud constraints, our algorithms was able to minimize the cost. The cost was reduced by 2/3 compared to renting normal VMs. And our successful approach should in general be able to reduce the cost of CPU-bound workloads, similar to the workloads we used, but it could be any kind of workload. Thank you for your attention.
Thank you for the presentations. Very nice talk. I have one question, and maybe other person will ask questions. So my question is, for example, if I can use a preemptive virtual machines for training a deep learning model, and if there is some interruption for 5 seconds or 1 hour, for example, is there some system for checkpoint to avoid restarting from new?
Yeah, that's a very good answer. Well, in this work, there was no such checkpoint.
Yeah.
So,
Okay.
so that would have to be built into the system. As of now, we are just mining, and this mining can stop at any time. So, okay. But the idea of checkpointing would be very important if you should run a general workload using these VMs.
So the user have to plan that before starting to work with the virtual machine.
Yes, but yeah, you get a 30-second notice, right?
Yes.
So and that's actually something we want to look at as an extended work or extension of this work, and that is to set up such a system so that it can move also the information.
Okay.
And restart elsewhere.
Okay. Okay, that's fine. Okay. I don't know if there is some other questions in public. So, okay, so thank you again for the nice presentation and for the answer. It was very nice work. So happy to share with you the other idea or discussion if in the future.
Yeah.
And I think, thank you. So it was the last presentations. I think that we can conclude the session. So I have to thank all the participants for the session, for the nice words, and for all the discussions that we had together. So I can